Alright, hell yeah. So what we have here is probably a pretty difficult angular momentum problem. So we have a bicycle wheel. It's a ring, you know what I mean? So all the weight's kind of at the end, you know, it's not a disc. Okay. And it's just like that, playing with the horizontal. Has a mass of 1 kilogram. Cool, I'm just going to kind of write that in there. 1 kilogram. Radius of 2 meters, you know what I mean? So American, it's going to be like 6 feet, 12 feet. It's really big, 12 feet. Holy, and if this is 2, it's only just like about 3 feet from the wall. So 12 feet, 6 feet, 3 feet. Cool. And this is 9 feet, basically. Alright, so with the, the rod is rotating. Cool. And so the angular speed of this is 0.5 radians a second. Now, you know what I mean? And look at this. The 1, 2, 3, 4, 5, 6. They kind of spell it out. At least they break this wheel up with, you know what I mean, 6 segments. Because one of those segments, 60 degrees is a radian. So we're going half of that in 1 second. So we're 0, 1, 2, 3, 4, 5, 6, 12 seconds all the way around, you know what I mean? So you kind of get it. If a wheel is also, it's also rotating this way, you know what I mean? And it's rotating with the same angular speed. So we're going to do 60 degree increments here. And this thing is rotating, you know, from here, it'll rotate what's 60? Yeah, so this is 30, 30, 30. So it'll rotate, it'll go, let's see, 0, here we'll go for this, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So yeah, it'll take 12 seconds to go that way. Basically 30 degrees per second. I mean, that's half a radian. Half a radian is about 30 degrees. Sweet. All right. So if a wheel, yeah, same. Now the rings plane, yeah, it'll actually stay parallel. That's just what they say. I'm wondering if that's actually like a property of this setup. You know what I mean? If you know, and if these are, they make it seem like, hey, if this is rotating with the same angular speed this way and that way, it'll stay parallel. But anyway, now it says find the angular momentum. This is always the trickiest one. It's just like where. Okay, so it says about the horizontal axis. About the horizontal. So horizontal is always like flat. So yeah. So like in plane with this horizontal axis, we get that. And we're passing through the left end of the rod. So about the horizontal axis. So, you know what I mean? If we have like a x, y coordinate system, x, y. Hey, this is going to be the axle passing through the left part of the rod. So this is a rod, and yeah, this rod also has weight. Let's see. Yeah, horizontal rod has a mass of 1 kilogram. Cool. Okay, so the rod has a mass of 1 kilogram, and the ring, you know what I mean? It's a ring, has a mass of 1 kilogram. Okay, sweet. So they want us to take the angular momentum about this axis, you know what I mean? Because it's horizontal. It's passing through the left end of the rod, and it's perpendicular to the rod. Now, that's where I just got confused, because, like, hey, you could have, anything could be perpendicular. You'd have something like that that's perpendicular to the rod. But, I mean, in your Cartesian coordinates, hey, even vertical could be perpendicular to the rod, but it says it's about the horizontal axis. So, we're going to do this one. Cool. And now, for the life of me, I don't know why you don't need this distance. You know what I mean? I don't know enough about rotational. What I think it is check this out. So let's say we did take the, because angular momentum, you know, if we do L, it's a vector, and it's a cross product between the distance and the cross product of the mass and velocity. Now, mass doesn't get a vector sign. but velocity does. So what happens is if I have this distance this way, only a velocity perpendicular to this distance. If I'm getting some sort of velocity this way, and I guess I kind of am, actually. Yeah, check this out. Like the center of mass, of this ring is right there, and we are going to be moving, velocity tangential due to this omega, because this whole thing is rotating up. So that's pretty cool, And we identify, if you identify a 90-degree angle, that's kind of what the cross product is. I did this in one of the other videos. Is like, this is really similar to torque. Torque is the same thing. A distance crossed with a force. So if we're trying to open a door and it's got hinges, then here's the handle, and we want to put a force this way. And guess what? Look at this. There's the hinges. So if we do this, if we're like, hey, I want to know the torque on the hinges. So I actually start at the hinge. I'm going to call this point O. And, same thing. We want to find the torque along this axis. So, hey, isn't that really similar to our problem? You know what I mean? And so what we're going to get, when you do the cross product, hey, you get a vector. You basically say, hey, check this out. So when I go, this is my R, this way, I cross it into this. So we do right-hand rule, fingers go this way, and then cross it into that. And then check that out. My vector is going to be perpendicular to this. Now, if I was just crossing this, we're going to call this R prime, and a velocity T prime. Well, hell yeah, that's really easy to see that we'll be in this direction. So over here, it's not quite as easy to see. So sometimes it's best just to throw in some. You'll have to know a little bit about statics, but we'll do some I hat, J hat, K hat, and just kind of do a little bit guesstimation. All right, so we'll go back to this one because we do have an R and we do have an F. So let's see which direction we want to go. Do we want to from the hinges, we're going to go this direction in the R, and I guess I'll do this force right here just so you can do the right-hand rule. So we're going to go this direction in the R, and we'll be perfectly perpendicular, and we're going to be going down. So, and then for this torque vector, if you do two arrows, I don't know where the hell I get this, but it's just like, I think this is kosher, or whatever. But hell yeah. So and I like it because it tells you, it's just like, yeah, this is useful because especially if you're trying to open a door and then you put like some sort of vector down the hinges, it doesn't seem like it's useful because if I put a force at those hinges, obviously that is not useful. There is no distance. There's zero distance. There's going to be zero torque. But yeah, so that's why I do this with double arrows. Same thing here. We can do this with double arrows. So then we can designate kind of the direction. Yeah. So even right here. It's like, man, I don't know. I'm just going to call this a 30-degree angle. This looks like 1 meter. They don't specify it. But if we wanted to find this angle, it would be hey, angle is inverse tangent of the sine component, cosine component. So it's going to be 1 meter, 3 meters. And let's go over that because tangent, you should always know. You should know sine, cosine, and for sure tangent. Because if I have this angle, tangent of this angle is just sine angle, cosine angle. And I think you can remember that. But then you just got to remember, hey, the sine component, the sun is shining. This is the sine component. This is the cosine component. Now, the sine component, it can be a couple of things. It could be if this radius is 1, kind of like the unit circle. Well, hell yeah, it's exactly that length. And the cosine component is exactly this length. Usually this isn't going to be 1, your hypotenuse. But if your hypotenuse is just h, just some number, then you just put that h right there. You know what I mean? That is the length. This component is the hypotenuse times sine of the angle. Cool, because if this was 1, it would... anyway. Oh, man. Anyway, so yeah, it's just a good one to know. And sine... So then when you do the... so then you can just know that tangent is like, hey, this side divided by that side. So if you know anything about this side and the cosine side, hell yeah, you're just good to go for the tangent. And then you just inverse tangent... And just I guess the take-home point is like, hey, the sine divided by cosine. I think you can remember that, and just sun is shining on this one divided by that one. All right, whatever. So so we have inverse tangent 1 divided by 3, and that's going to be an 18 degree angle. Do we want to use 18? No, we're just going to say this is 30 degrees. You know what I mean? So whatever makes this 30, cool. And, hell yeah. Alright, so, and if this is 30, yeah, so, you know what I mean, this component, we need something. So this is x, this is y, and this is going to be our z component. So this is going to be our I hat, this is going to be our j hat, and this is going to be our k hat. And, let's see, so we're going, I'm just going to call this 0.866 j hat, and then this is 0.5 I hat. That would be a 30 degree. You know, cosine is 0.866. The sine is 0.5. All right, so that's going to be my distance vector. So we're gonna take, and we're gonna cross that into a velocity vector that is kind of similar, but it's the opposite. We're gonna have 0.866 in the j, and then we're gonna go negative 0.5 I. So sweet. So let's do that. So we're going to have this distance vector. It's going to be 0.5 I plus 0.866 j. And we're going to cross it in to something that's negative 0.5 I, and then plus 0.866 j. Now, is that right? This is 0.866 I. I don't know what the hell I was talking about. I knew something was up. And if we're calling this the j direction, this was 0.5 j. Cool. So whoops. And this is I. Okay, so I think now we're good to go. And then so to cross these, the simplest way is to do I, J, K, I, J, K. I just came up with this one, you know what I mean? Because then if we go in this order, I to J, J cross K, K cross I, you know what I mean? And then it just repeats. You can do it again if you want. Just because you'll have to go I cross J, J cross K, and then kind of wrap around K cross I. But this will give you positive. If you're going that direction, that'll be positive. Cool. So we got first one, J cross I. Well, that's going the opposite direction. So we're going to have a negative. So we're just going to do a negative. And then we have 0.5 times negative 0.5. Cool. And if we have J cross I, you're just going to get a K. Cool. All right, so and then you're going to have J cross J. You can't do it, or you can. You can cross J with J, but hey, if you have something going, if you have, this is cool, because if you have the I, J, K, if this is X, this is Y direction, and this is Z direction, you know what I mean? And then you got two things going in the J direction, and you're going to cross them. Well, hey, they're going in the same direction. You know what I mean? A cross product is like a torque. You know what I mean? if you have this distance, and then you tried to pull on the door this way with a force, well, hey, your distance and your force is going in the same direction. You ain't torquing nothing, you know what I mean? So that's where people are asked of like, well, what the hell is a cross product? Well, it definitely is a torque, a moment, and it's a first moment if you're just taking the distance and not squaring it. If you square the distance, it's going to be a second moment, you know what I mean? That's kind of the difference between a moment and a second moment. I guess you could have well, let's just leave it at that. Cool. So this is a moment of mass and velocity. See how this is? We have a force, but we're doing something with it. We're moving the force a distance away from the thing that we're trying to you know what I mean, to do, and we're putting it perpendicular to that distance, and that generates torque. Same thing here. Angular momentum is, how did I say it the other day? You know what I mean? So if we do have some sort of mass and velocity, you know, even from this, well, let's like take out the wheel, and you just have a rod with mass, and then at the end just stick that other mass right there. So you have a rod that has a one pound rod, center of mass in the middle, and then this is 1 pound. So you got like 2 pounds, and it's going this way. You know what I mean? And it's just spinning around this circle. Forget gravity and all that. But if you had to slow that down just by pinching on this axle, that would suck. It would be really difficult. So I always think of that. I think that's a good representation of, like, if this thing, and even if you just come here, if you throw out a little spindle on it, and this thing is spinning, and all you get to do is like pinch, like, and try to stop that spin, you're gonna have to pinch really, really hard. You know what I mean? Pinching is about the worst. You know, it'd be like, hey, if someone was closing a door, but you could kind of pinch the hinges together. I don't know, like, and to try to stop them from opening and closing the door, like that's a good way to visualize that. Hey, there's a lot of torque in opening a door. There's a lot of mass and velocity, you know what I mean? And so we call this momentum. I think you could also call it inertia, but mass and velocity. But it's not only mass and velocity. You know, if I have a baseball and I'm the catcher, you know, and I got my mitt out, cool. I'm gonna catch that ball, and I'm going to stop its mass and velocity. You know what I mean, right? But you know, with this, if I'm going to stop this wheel, you know what I mean, obviously, and let's say this wheel, like, let's say the mass is just like, let's say it's just this. It's a massless rod, and then the mass is just on one end, and that thing's spinning around. Same thing as that baseball. Hey, let's say I put my catcher's mitt right there, and booyah, we just catch it. And that would be the same thing, you know, turning angular momentum problem into just linear momentum and catching that momentum. You know what I mean? You're probably going to have a force on it for sure, because your F equals ma. You know what I mean? This had velocity, and then it had zero velocity, so it must have had a change in velocity with a change in time, and it is a mass, so therefore you must have exerted, you must have put a force on that. Hell yeah. Alright, so I think that could be my forte, is just like really hammering home, you know, turning even angular acceleration problems into F equals ma. But okay, so but this this isn't how you get to slow down this wheel. Like, I think you just come back here, and then with 2 fingers, you know what I mean, you start to pinch that wheel. You know what I mean? Good luck. I mean, this spindle. You know what I mean? Hey, this chunk of mass is going around, and then it has a spindle up, and then you got to stop this chunk of mass just by, well, man, you know what I mean? That's going to be a way harder, and then you're going to get this general idea of what mass and velocity and the moment of mass and velocity. That's angular momentum. You have some sort of mass out here, it's got some sort of velocity, and hella some sort of distance away from an axis of rotation. You know what I mean? That you would try to stop that mass from that location. The same thing is if check this out. You know what I mean? Let's say you're on one side of a river, and you have a board in your hand, and you have to like hold that board. I don't know why you would have to hold it. But and then somebody, and then you got a river here, right? And then someone else has to walk across. You know what I mean? So they're gonna step on here. Well, that's gonna hella suck. If you just have to hold this above ground, like I don't know why you'd have to do that. But that is literally the definition of that's the definition of torque. You'll have to put a torque. Is that the definition of torque? You'll have to put a moment. You know what I mean? I guess if this is a statics problem, they call this a moment. Which yeah, it's a torque. But you basically you have to put a moment on that. You know what I mean? A couple or whatever. And here, hey, look at this. You had a force and then a big distance from the hinges. Here, this is literally like, hey, your hand is just right on the very end of it, and then you are the hinges. You know what I mean? Like if you had to do this in real life as like a problem solving thing, like holy hell, what you'd want to do is get one hand like way far, as far, underneath this plank of wood, and then your other hand just like straight down. You know what I mean? So you're applying a force that way and a force that way. Cool. And this is the moment that you're generating to keep this thing up. So then when someone stands on this side, you're like, holy hell. You know what I mean? Maybe you could do it. Probably not. I mean, obviously not withstanding, but maybe someone could put, something like a bag of sand on that side, and maybe you could do this. But if you have to do all this stuff with your hands at the same location, very much like pinching a spindle, like good luck. You won't be able to put any weight, hardly any weight on the end of that. And so this is a really good representation of angular momentum, because angular momentum can be taken from any point. You know what I mean? It can be it's kind of interesting. You know what I mean? So well, let's say, let's just say you have like a big chunk of mass, and it's on a massless rod, and it's hella moving in a circle, and here's its hinge, and actually you make the hinge. You know what I mean? So you also pinch with your hand, and you have to hold that pivot while well, I guess two different things. No. Yeah. One is just, hey, it's moving with some sort of velocity, an angular velocity. You know what I mean? And then you have to pinch and slow it down. Bring that to a stop. Well, you know what I mean? Because it has mass, and it has tangential velocity, and it has this huge distance. You know what I mean? So if you did that same scenario where you just had that same mass, but just like right here, and I don't know. Let's say someone gave it a head start. You know what I mean? Someone like just like gave it a kick or something, and then they kicked this vertical, and then you had to see how fast you could stop it. And obviously this is a horrible representation, because we can't escape the earth, so doing this in the vertical is so dumb. But you'd want to do it in the horizontal. You know what I mean? So hey, have someone kick it horizontally where it kicks at a tangential velocity that way, and then you, like, here's your spindle, so you actually have to pinch it this way, and you have to keep it from rotating. You know what I mean? Like, bring that to a stop. Someone kicks it tangentially, and then you got to bring it to the stop. And I don't know, even these two scenarios don't really do it justice, because if someone kicks this at the same velocity, I don't know. It seems like it's going to suck in both cases. So maybe that wasn't a very good representation. But, yeah, it's just interesting. Yeah, this is a horrible representation, because even my mind is just like, well, it seems like the longer one's going to be easier to stop for whatever reason. And but no, it's the opposite. So anyway, so the farther you are away from that mass and that velocity, and then you have to pinch, you know what I mean, a little spindle to keep it, to bring it to a stop. The farther this distance is away, and then how you have to pinch that spindle to bring that to a stop, that's going to suck. And the closer you are, heck yeah. And, the closer you get to pinching this rotational spindle, it is then synonymous. Like, if you get so close, it's just like catching it with a catcher's mitt, per se. You know what I mean? I think, you know what I mean, it seems like there's a little bit of a miss between rotation and pinching a spindle to just actually catching it. Alright, sweet. So that's a pretty decent introduction, and I really enjoy showing how torque is very similar to angular momentum. Cool. And so, yeah, in angular momentum, you can pick a point that's not even attached to the system. You could pick a point out here and be like, what's the angular momentum from that point? You know what I mean? I think it's like if you, it would be like, hey, if you did attach, if you were able to, like, hey, take that chunk of mass that's maybe spinning tangentially that way, and then you have to, like, hey, take a huge stick, and then put your catcher's mitt at the end of this stick. Okay, there you go. And then you can't even hold on to this stick with two hands. This stick has a tiny little spindle that then you also have to pinch with your finger. It's like, that's gonna suck. You know what I mean? So yes. So I think I did it justice right there. So this is why angular momentum is a bizarre one, because it's just like, hey, it only says, and this is where I think I can actually add, like, I can have skin in the game of really making angular momentum make way more sense than just, like, I compare it to energy, where it's just like, once you learn the energy equations, you just lose all sense of F equals ma, and just all sense of what the hell's going on. But if you stick with these fundamentals of, like, hey, I have mass, like, you know what I mean, and then I have some velocity, well, all it's saying is, like, yeah, then you have, it's going to be hard to slow that down in this case, in that case. The easiest way to slow it down is just catcher's mitt and then hit it, in the direction it's going. And if you do this, like, if you're finding the angle, so if this is the only thing that's moving, to keep the problem simple, you just have a mass on a massless rod and it's spinning around here, and then you decide to just have the catcher's mitt right there. That's the same thing as saying, hey, let's take and then let's say the catcher's mitt and this whatever mass is just the same location. And so now visually it's just, we're going to put a dot right where that mass is, and then we're going to find the angular momentum of that dot. Okay, so, and right now the only thing that's moving is this mass, and it's moving that direction. Cool, so let's start taking the cross product of mass and velocity, and guess what? Okay, so we've identified the mass, hell yeah. We've identified that it has some sort of tangential velocity, hell yeah. And we're even, but now, how the hell, like, how the hell do we actually travel a distance? Because we're saying we're occupying the same space as the mass that's moving. So from that point there's zero angular momentum. So catching a mass that has velocity in a linear path, hey, then that has zero angular momentum. There is no stick and a spindle, and then you have to pinch anything. You know what I mean? You don't have to hold this catcher's mitt out with a stick that has a spindle that you pinch. You know what I mean? Because even if you stood 1 meter to this side of it, you know what I mean, and took the angular momentum here, well, hell yeah, things change. You have to take that catcher's mitt, put it on a spindle, put it on a stick, and then put a little spindle and start to pinch it, and then you have to catch this mass and velocity by pinching that spindle. And then you'll be like, oh, hell no, that sucks. And then the suckier it is, the bigger this number. You know what I mean? Hell yeah, I'm pretty proud of myself. I think that was a pretty good explanation. Alright, so hell yeah. So the first thing that we're going to do is, I think you just break this up into a couple parts. I have no idea. Because, let's see. And, oh yeah, this is interesting. Okay. Yeah. I mean, because, yeah, let's just grab a fresh sheet of paper. I mean, let's say we actually just really wanted to simplify this problem. We could say, oh man, sorry about that. We could say that this rod has a mass of 1 kilogram, and then this whole thing has a mass of 1 kilogram. We just put it right there. And I don't know, maybe we just... Alright, hell yeah. So, you know, and I haven't done too many problems with rods to actually make a simplistic model. But we're just going to throw the whole mass in the middle, you know what I mean, and call it good. You know, if we didn't have this as a mass, I'm just going to... The whole mass is right there, and it's probably not representative at all. It's probably actually a pretty horrible guess. But now we're just gonna go to this point, and now that we're just going a distance this way, so let's do our coordinates. So we have I hat, j hat, and then if we do, so yeah, anytime that you have the I and j, go into the I or the x direction and y direction, and then hell yeah, that shows your thumb will be in the k direction or the z direction. Cool. So we're gonna do angular momentum is r cross mv, and it should be kind of obvious that if we go, well, maybe it's not. So this angular momentum is the only one. This angular velocity, I'm sorry, and is the only one that we're paying attention to. So we have a tangential velocity there. We're gonna call it vt prime, and then we have a velocity tangential here. Cool. And you know what I mean? We're just gonna get just a general gist of what's going on, and maybe it's very close to one of these numbers, you know what I mean? Because we're still tackling this problem for like, hey, let's see if it's on a test and stuff. So this could be like the first thing that you just do, just to be like, oh, what the hell? All right, so and then you can see that if we go this distance, this r vector out to there, we're totally going to be here. So I'm just going to do the double arrow thing, and this will be our angular momentum. Cool, and it will be in the k hat direction. Hell yeah. So so if we do r cross velocity tangential for this first one, we're going to be 1.5 meters. And then we're going to multiply it by the mass, that's 1 kilogram. And then we got to multiply it by the velocity tangential. We know this is 0.5 radians per second. So tangential velocity is, you know, if I have 0.5 radians per second, no one knows what radians per second is. That's kind of, so I use it as an equation. Like radians per second times radius is something normal, and that's going to be the tangential velocity. That's going to be Vt, and our radius is going to be 1.5. So cool, we got 0.75 meters. Oh, excuse me, per second. Alright, so 0.75 meters per second. That's just for the first one. Like, hey, we're done. No. Yeah, no, we're done. I mean, because obviously we would have done 0.5 times 1.5. So this equation becomes R M omega R. So this is the classic, hey, you combine these two terms and then so you go mr squared omega. But why the hell would you do that? You know what I mean? If classically you're going to be multiplying, you're going to do the cross product. You're going to be like you're going to do distance times mass times you know what I mean, omega r. Like, you know, you might as well keep it in this form. I mean, or you should at least do it in this form so much that's why this form you lose. You're kind of like, what the hell? Why would you collect all those terms? Well, we do that because this is the definition of second moment of mass. You know what I mean? And we'll see if I can even do this problem without second moment of mass. That's my goal. Is just like, because if you're going to use moment of inertia, second moment of mass, mass moment of inertia, whatever you call it, yeah, I think you lose the fundamental understanding of angular momentum problems, where you lose the idea that it's just these three terms and at a perpendicular ness. You know what I mean? Alright, hell yeah. So I took a little break, but we're back. And, you know, I coined a term, right? I think I want to coin this term, you know what I mean? Leverage of mass and velocity. So what is angular momentum? You know what I mean? I would say it's leverage. I'll even write it down. I usually don't do this. Leverage of mass and velocity. So if I got if I have some sort of mass and velocity, you know what I mean? Hey, it's like the leverage of it. You know what I mean? So if I have this mass going this way, it has way more leverage than this mass. You know what I mean? So I think I'll come up with better now, but I think this was pretty good. Holding a bridge, that's an impossibility. You know what I mean? You can hardly hold a 2x4 vertical by holding the end. You would have to do something like this. You know what I mean? But get real. You throw a tiny spindle, and then, you know what I mean, something like a... Yeah, I don't know. I think for like like something like this, if you had a like a bike handlebar, you know what I mean, just a totally flat bike handlebar that you had to grip, but no grips. You know what I mean? Just the metal on. You know what I mean? That would still be difficult. I guess even if you put grips on it, you'd probably be able to double what you could. No person's gonna cross that because you just have so much leverage. And where's the leverage here? It's force times distance. That is the leverage, and that is the definition of moment or torque. You know what I mean? Yeah. And I guess what is this? Is this usually moment for leverage? This is the first moment of force. So we identify a force and we say, hey, it's a distance away. So that's what makes it a first moment. You know what I mean? It makes it a moment of force, but it's a first moment where we'll get to it later. But yeah, this I just want to stay away from the term for now. But the second moment of mass, you know, is I. We take you know, if I have, for this problem, if I have a ring and all the mass is on the perimeter, hey, here's my radius towards it. But if I want to know what the second moment, and this is the second moment of mass, if I want to know that term, I have to identify the mass. That's going to be in kilograms. And then I'm going to, or just m, and then I'm going to take the distance squared away from it, and then so for our problem that's going to be mass r squared. So in taking that distance twice, or you know what I mean, squared, is where that second moment comes in. It would be the first moment of mass if you just took mass times distance. That would be the definition of first moment of mass. So angular momentum is a first moment of mass and velocity. You know what I mean? The second you get into second moments, holy hell! You know what I mean? Things that's a squared parameter where that thing can be a big driver. But then you see this is a first moment of mass and velocity. But that's the crazy thing, is that if you have angular velocity here is angular velocity times radius. So you could say, I don't know if you could say this, because these two distance terms, do not confuse those. Those two distance terms sometimes are not the same. You know what I mean? So you can't just have any generic mass in a distance of way and then some sort of tangential velocity. But in your generic cases, where sure, there's plenty of times where these two radiuses are the same. There's also times where these, I guess just distances, these two distances or radiuses from some point are the same, and there's times that they're not the same. So I guess from the standpoint that these two are the same, well, hell yeah. Then what do you have? You have mass and angular velocity, and then you're going to r squared. You know what I mean? So this, just like you would write mr squared, or md squared for second moment of mass, where you have a mass and then the distance squared. Well, hell yeah! This would be the second. This would be the second moment of. So angular momentum is the first moment of mass and velocity. Cool. This could be but angular momentum, I guess, could be considered the second moment of mass and angular velocity. I have a really hard time saying. I think most people have a hard time saying angular velocity. I've noticed in just a lot of videos they just call it omega. You know what I mean? And then they hardly ever call it angular velocity, just because it's difficult to say. You kind of have to remember, you know, how to say it. Angular velocity. All right, hell yeah. So I think that covers what angular momentum is. It's leverage of mass and velocity. Cool. All right, so let's go back to our problem right here, and yeah, we were on our way, and then we got kind of sidetracked. So we did this one, you know what I mean? So this is going to be 1.5 times 1 times 0.5 times 1.75, or 1.5 times 0.75. Cool, I don't even know what that is. 1.5 times 0.75. That's gonna. So this part's gonna be 1.125. Cool. All right, so now let's do this one. Hey, we have the same 1 kilogram, but it's way far out there. You know what I mean? So now we're going to say the distance is 3 meters, 1 kilogram. And then we have the mass. No, we just did the mass. We have the velocity, which is omega r. So we did r, m, omega r. And then you see how this distance comes up twice. So yeah, when I said, oh, this is way out here, hella, well, because it's going to be a distance squared. So what's the difference between 1.5 squared and 3 squared? So we're going to take 9 divided by 2.25, and we get 4. So double the distance, you get 4 times the leverage. You know what I mean? Put this on a spindle, holy hell, it is going to take 4 times ridiculous to stop that, you know, pinching a spindle. Alright, so where were we? So we got distance of 3, mass of 1, and then we have that 0.5 radians per second, and then we have that distance again of 3. So now we have 6 times 0.5, half of 6, that's 3. So we get a value of 3. And so right now, hell, we have a guesstimate, 4.125. So which one of these is pretty close to that? Well, that one's fairly close. What is this? You know what I mean? No one knows what square root of 10 is, but what's square root of 9? Square root of 9 is 3. Hey, so this is going to be about just a little bit bigger than 3, but 3 times 2 is 6. Call that 6. So maybe this is just a little bit bigger than 6, 6.1, 6.2. All right, so we got 6, 6.1, 6.2, 7, and then 14. So even just right off the bat, like our estimate was like, hey, maybe this is closer to 4. But check this out. We did a trash job of doing what a rod is. Because check this out. Because a rod, this whole thing at 3 meters it is going to be 1 kilogram. So let's break it up into two sections. And we're going to say, hey, half of it's right here, half of it's right here. Let's find the angular momentum here. So we're gonna do it. Let's just do it a little bit faster. So angular momentum is r cross mv. Okay, so we still have that omega, and we can find our velocity tangentials. I'll call that velocity tangential prime, velocity tangential. Cool. So these I'm just designated that these are different. You know what I mean? Cool. Let's do it. So we have the distance to here. If this is 3, this is gonna be 1.75. So we got 0.75, and I ain't putting labels on. So 0.75 times the mass is gonna be 0.5. We're just doing half, and then we're gonna break it up into 4 or 3. You know what I mean, and keep going. So and then we got omega 0.5, and then we have the distance again 0.75. You know what I mean? So we got 0.75 times 0.5 times 0.5 times 0.75. Alright, sweet. I got to store these as alpha A. You know what I mean? That's 0.14. Cool. Let's move on. And then we got this one. Hey, this is like 3 minus 0.75. This is 2.25 times 0.5, that mass, times the omega, times 2.25. So at a certain point, you'll do this repetitively so much that you'll just be like, well, let's just square these. You know what I mean? Let's just say this is r. Instead of saying it's rm omega r, well, let's literally just do what I didn't want to do. You know what I mean? You could just do it r squared m omega. You know what I mean? Do whatever feels right. If you're going to take the distance first and then square it, then take the mass and omega. You know what I mean? You can do it in whatever order, but mr squared omega is typically the order that you would do it because this is I omega, and that is angular momentum. Anyway, cool. So we got 0.25. Let's just do that. 0.25, we're going to square it, times 0.5 squared. Hell yeah. So we got, and I'm going to store that as alpha B. Okay, so now we got alpha A plus alpha B, and this generated an angular momentum of 1.4, which is definitely bigger. So this is what we got, 1.25. So now let's chop this up even more. So we're going to chop it up here, and now we're going to get a quarter of a kilogram. And you know what I mean. And these distances suck. You basically have to divvy it up 3 divided by 8, and then say, and I'm even going to store that as x. And this is going to be 0.35. So we're going to have x squared. That's going to be this 0.375 to that one. X squared times 0.25 is our mass, times 0.5 is our omega. So what I did is I did it in this order. R squared, our mass is 0.25 because we got 4 of these masses. Basically just trying to figure out, like, what is this term gonna, approach? It's gonna be bigger than what we guessed by just throwing the mass in the middle, is because this mass on the end is gonna move way farther, and we're doing the radius towards it, which we're gonna square as again. You know what I mean? So yep. And so we're doing this r squared m omega. Cool. So I'm going to store that as alpha A. Now we're going to move on, and we're going to do 3x, and then we're going to square it times 0.25 times 0.5. Store that as alpha B. So that was that term. Now we got to go 1, 2, 3, 4, 5x. So we got to go 5x squared times 0.5 times 0.25. Store that as alpha C. And then we got to go 7x squared times 0.5 times 0.25. Sweet. Store that as alpha d. So now we go alpha a plus alpha b plus alpha c plus alpha d. Hell yeah, we get 1.47. You know what I mean? So you know, we're not crazy increasing. You know what I mean? This parameter. So, but check this out. I think that we might be misrepresent. So yeah. So let's just call this 1.5. So we're going to call this 1.5. And we're going to say, hey, now we're up to at least 4.5. You know what I mean? So, you know, we're shooting between A, B, and C. D seems too high, way too high. Okay, so, but instead of this 1 kilogram mass right here, hey, this could be a 0.5 kilogram mass right here. And a 0.5 kilogram mass right there. You know what I mean? So and then so we'll do it this way, and then we might break it up into quarters. Hey, we could say there's a quarter here, a quarter there, and then a quarter there, quarter there. But and hopefully I'm getting. Let's see. The ring is 1 kilogram. The rod is 1 kilogram, and that's it. Cool. Alright, but check this out. So now this is going to be a distance of 5. So remember how we said, like, whoa, like hella? You know what I mean? We're going to do that 5 squared. So let's do this one just right away. So we're going to do that one first. We're going to go 5 meters squared times 0.5 kilograms, and then times omega, right? 0.5 radians per second. And doesn't that get us there? Because we have r squared m omega. Sweet. So we got 5 squared times 0.5 times 0.5. Yeah, damn. That's already 6.25. Holy, so this one might be in. You never know. You never know. All right, so yeah, wasn't that wild? Just even moving that to there, knowing that, hey, instead of a ring, it could just be 2 masses that are going, and when the masses are out here, heck yeah, they're going to be representative of that. All right. Cool. So 6.25. Keep that in mind. All right. Now this one is going to be only 1 meter away. So it's basically where I put. No, this is going to be 1.5. This is going to be 1 meter. So now we have 1 meter squared times 0.5 kilograms times 0.5 radians per second. Does that do it? R squared m omega. So now this is just going to be 0.25. Cool. So we get a total of 6.5 though. You know what I mean? If we did that, this would be different. This would be 6.5. and this is probably like 1.5. So we're going to have 6.5 plus 1.5. And so that gets us up to 8. So, hey, maybe this is a pretty good representation at 7. I still don't think D, and, you know what I mean? I still can't prove that it's not more, I can't prove that it's more than 6. You know what I mean? I can assure you that the angular momentum of this is at least 5. And then, the angular momentum, you know, and let's go back to, you know what I mean, just the world that most people live in, is that if you have a rod like this, your I is 1/12. What was it? Yeah. So what is this? It's ml squared. You know what I mean? So the I is going to be mass. What was the second moment of mass? You know what I mean? So we have some sort of mass, and then it's a distance away from L. And then we add all those up, and so we have a mass and a distance away from L. But that length is squared. That's why it's the second moment. So that's why that looks like that. From the pivot point of a rod, you get 1/12 ml. But if you take the pivot point over here, you get 1/3. Is that right? ml squared. So now I just know my I is 1/3 ml squared. You know what I mean? So I know it's 1/3. I know my mass is 1 kilogram, and I know my length is 3. So cool. So my I term is just going to be 1, and then my omega term. So Oh, that doesn't sound very exciting. Oh no, I always space these. Anytime I see a square, this. But hey, I did a pretty good job of like that didn't seem right. But no, it's the length squared. So we're gonna have, we're gonna have 3. You know what I mean? So one of these 3's cancel, and you're gonna have the I term is 3, and then you have to multiply it by the omega term. So for this is going to be 3 times 0.5, and hell yeah. So my approximation was right on. That's 100% accurate doing it like this, and then even divvying it up in 2, we did it in 1 and we got 1.125. That's pretty horrendous. You know what I mean? That's going to be error, but just even chopping it up into 2 pieces and putting the center's masses right there got us fairly close. We got 1.4, and it approaches, 1.5. All right, hell yeah. So, hey, let's. I think that was the other thing that we wanted to do. Let's grab a fresh sheet of paper. So we wanted to throw a quarter, a quarter, and a quarter. Hey, that's pretty representative of a hoop. You know what I mean? So we're gonna have 0.25 kilograms for all these. This we already know is just 1.5. We already did it. And what's the angular mass of the rod? From that is going to be I omega, and then the I was 1/3 ml squared omega, and so that's 1/3 point. But see how you don't learn anything? You know what I mean? Just by memorizing equations, you're not going to learn the fundamentals of what the hell leverage is, what's leveraging. You know what I mean? You're just not. Unless you break this up into components, and then so my question is just like you do center of mass. I mean, like that's going to be for a separate video. I'm not going to go over center of mass right now. Well, I mean, you could. I mean, yeah, it was like, hey, you have a 4 right there, and then a 1 right there. It's like where's the center of mass? Well, you exactly. I don't want to go over it right now. But if you know how to do center of mass, cool. But yeah, the same thing here. At what distance x do I put this 1 kilogram to equal 1.5? So let's do that. So my angular momentum is going to be the distance squared, x squared, times the mass, 1 kilogram, times omega. You know what I mean? This was a better representation. R squared m omega. That makes more sense to me than m r squared omega. You know what I mean? Like I omega. Just because we do the r cross mv, and you do the r first. Hey, you go distance r, and then from this term, yeah, we know that it's omega r, and then I'm gonna square it. Cool. All right, but yeah, just right here. So now we're going to say this was 1.5. We already found it, 1.5. And so now we're going to take 1.5, and now we divide by 0.5. We multiply by 2. So we get 3. So yeah. So we get 3 is equal to x squared, and then x is going to be the square root of 3. So the distance is the square root of 3. Oh, so I can keep that in mind, you know what I mean? Hey, if I have a rod that has a length 3, where am I going to put, and it has a mass of 1, where am I going to put this where it's representative of a rod? Well, it's going to be at 1.7. So if this is 1.5, we just do 1.7. So that's where it is. It's not even right there. So me putting it in the center, hey, it was actually fairly close because you really don't have to move it too much because of that x squared term. Because this is r cross mv, and because it doubles up with the other r and omega r. Yeah, so like, yeah, and again, this is the skin in the game that I can help, with simplifying angular momentum problems. Hey, let's just get it to a chunk of mass on a massless rod. You call it a string if you wanted to. And hey, but a massless rod works because then you can put a spindle on it and you can pinch it. And you can be like, well, how much juice, is it going to take to actually stop that thing? From my position. Cool. All right, so I think we're going to have really good luck with this one. So we're going to do that same equation. I like it. R squared m omega. Perfect. And so for this, we're And we can do it all. Like, obviously, we already know this is 1.5, so we're going to have 1.5. We're going to do maybe this one first. So this one is at 1 meter out. So we're going to have 1 meter. 1 squared, 0.25, and then 0.5. So that's going to be, I'm going to do 1.5 stored as alpha A in my calculator. 0.25 times 0.5 stored as alpha B. Cool. And then we can do this one. It's just going to be twice. I mean, I shouldn't have done that until I'd done one, and then we're double it, but whatever. We're on a roll. So, and this is going to be a distance of 3. So we're going to do 3 squared. Don't forget that. That's 9. And then the mass is 0.25, and omega is 0.5. So we got, we'll just do the 3. We'll do 9 times 0.25 times 0.5. So this one was going to be 1.125. We got 2 of them. And I'm going to store that as alpha C. Alright, so this was alpha A, this one was alpha B, both of these were alpha C in my calculator. Now this one's out 5 meters, and so we got 5 squared, and then 0.25 times 0.5. So this is the mass, and this is the omega. So we got 5 squared times 0.25 times 0.5. Alright, and so we're going to store that as alpha D. And we got 3.125 as alpha D. All right, and so again, like my thing that I can add is like, you know, like using numerics. You know what I mean? If this problem didn't have numbers, I would put numbers and masses to them because I have some sort of understanding of what those masses and numbers are. And I mean, just throwing numbers at it, simplifying it, and trying to get, you know, some of the answers without doing it like 100% perfecto. And I don't even know how to do this one. I might make a huge assumption error. That's the only thing where it's just like you can assume, because you have to assume quite a bit. I mean, just to kind of learn. I mean, you like at the end of the day, you might just be assuming that I omega is angular momentum. You know what I mean? And you're right, but you might not understand the backing of that. And still, it's even a scalar quantity. So you get to here, you might be messing up the aspects. You know, you might have to use a cross product. All right, so what do we get? What do we get? You know what I mean? So we got alpha A plus alpha. Oh, do we store it as D? Sure. Alpha A plus alpha B plus alpha C plus alpha D. And hell yeah, we get 7. You know what I mean? So this is so cool because I think this comes up in textbooks a lot. Where if you have a hoop, yeah, so the answer is B, and I'm going to stop here because this really shows it. Because I haven't made the video yet, except the 6.5-hour JEE problem, where I turn a rotating disc into this shape. See, you know what I mean? The shape. If this is 4 kilograms. I say this is 2 kilograms, this is 1 kilogram, and this is 1 kilogram. Now, obviously, like this is at the radius, and these are point masses. But a circle is this. If you have any disk, yeah, and I think this is going to work with every single, like, yeah, it's so simple. You know what I mean? Because that was the thing is rotational, angular momentum problems, for whatever reason, like spook the hell out of people. Well, yeah, and I watched some of the videos, and it's just like, oh, the jargon is just ridiculous. When all you're showing is you have a mass, and then you have leverage. You know what I mean? Let's throw that up there. Leverage of mass and velocity. It doesn't matter where the hell you are in the universe. If you and the system has some sort of mass and velocity over here, hell yeah, get out your wooden dowel and then throw a catcher's mitt, you know, on it, and try to stop some of those molecules of mass. You know what I mean? That are moving in a tangential direction. You know what I mean? Just at that moment, and do your spindle and start pinching it, and you'll be like, no, that's hella. That's going to be hella angular momentum. All right, so yeah, and then so this problem, I'm just saying, hey, this I think is 100% representative. You know what I mean? But I'm second guessing myself because you just never know. You know, it might not work in every scenario. But for the scenarios that I've been using it, it's just like, whoa, yeah, you shouldn't think of a disc as a disc. You should think about it as 3 masses, the one in the middle being twice, and it's totally representative of a disc. I'll be doing more problems on that. Just like a rod. Well, cool. Now, I didn't even know that. I bet you no one's even solved for that. Hey, like, well, what's the equivalence of a rod? Yeah, I swear, it's just like that. I've never seen an equivalence problem. Just because everything goes to I omega, and then, you know, and the vector equation is good. I actually would prefer people using the vector equation compared to just the scalar version. But yeah, so yeah, taking a rod and figuring out, and this is that was new to me. If I have a rod with a length of 3 meters, I know that I can just say that it's a massless rod and a mass at a distance of square root of L. Like, that's amazing to me. And I think, you know what I mean, I'll have to do this more, but the more problems I do, the more that I can bank on it. And I don't even know what the answer is. I'm just totally assuming that that's the correct answer. But I can bank on, but I have seen this. You know, I have seen where I think I've seen problems. Well, I've definitely seen problems where they throw masses in a circle at 4 different locations, and I think they probably do relate it to a ring. You know what I mean? So because it's just 100% accurate. You know what I mean? This is my doing, and I think that's my an addition to you know, helping out people learn momentum, and hell yeah. And this one was a new one. So these 3 were kind of the take home parts for the momentum, where you turn it into something simple, and hell yeah, you can see the mass and you can see that it moves tangentially. Now you have to be oh yeah. So yeah, we'll finish with the cross product, because here's where this distance doesn't matter. This comes up a lot. So let's say I did find this one, and really its velocity is kind of more. So if this is the, should we do a new sheet of paper? Hell yeah. So we have these coordinates. I gotta get a new battery, else my camera's gonna get fried. Alright, hell yeah. So we're back. And we're just gonna go over cross product. So we're gonna do those 4 masses, but we're just gonna do one, you know, where we're gonna go all the way out to that one. Oh, excuse me. Alright, so this is 5 meters. We're just gonna say this is 1 meter, you know what I mean? So this is our R, and then the tangential velocity. So we're gonna do the coordinate system. So we have the x coordinate system, the y, and then we have the z. And again, you put your fingers in the x, go up to the y, and that's going to be your positive z. So there you go. So this is positive z, positive x, positive y. This is also I hat, j hat, k hat. Okay, so when we do the cross product, so angular momentum is R cross mv. Cool. So we identified a mass. We know it has velocity, and its velocity is in the negative k hat direction. Cool. And and then we're crossing it. So our distance, we're basically going in the I direction. So let's say we're just going from the I cross negative k, and you know, and we do the I j k, I j k, and so we're crossing I into k. You know, don't worry about the negative parts yet. So we're going to do I into k is not in order. I goes into j, j goes into k goes into I. So if we go I cross k, that's not in order. It's going to be negative. So do a negative. And now we're going to have I, so that's going to be like a positive I. Oh, what the hell am I even doing? whatever. This is 1 and this is -1. You know what I mean? If you can think of it like that. So now we have the cross product is still just a multiplication. So it's 1 times -1. And so there you go. Sometimes I do those first. I say, hey, if I have 1i and -1k, I'm going to do the multiplication. I'm going to go 1 times -1, and then I'm going to say I cross k. I cross k is negative. So I'm going to do -1, and then I cross k is j. So cool. And then I'm going to say, hey, that's just positive j. And is that what I get? Oh, I think I did the problem hella wrong. Oh, you know what? You know what? This is interesting. Because this, oh my gosh. Okay, I'm totally spacing because I'm doing this omega. Yeah, this answer might be 14. You know what I mean? So this velocity's got two components. Sure, it's spinning this way, but it's also going up. You know what I mean? We know that distance, this velocity t, I'm just going to call it velocity prime, and I'm going to call this omega prime, and this is going to be your omega. But omega prime is the same as omega. Cool. And so this velocity is going to be that 5. You know what I mean? That's going to be omega r is going to be 0.5 times 5. So that's going to be 2.5 meters per second. That's going to be the tangential velocity this direction, and that's going to be in the j hat direction. So that's the one that we were calculating. So let's go back to this. So we were saying, hey, if I have so let's do it. So if I do r cross mv, I'm gonna do this. R is gonna be 5i plus 1j crossed into the mass. The mass just gets factored out. But now my velocity for this one is going to be j. Cool. So I'm going to have a j component. But we can already rule this one out because that was in the j direction. So you would have that as your angular momentum. So we said angular momentum, but this is in the j direction, and they don't want that. They asked, find the angular momentum of the system about the horizontal axis. So any of these masses moving in this direction or even this direction, you know what I mean? So let's well, we have to cover our bases, but let's go back to this one because we were on a roll. And so the velocity of this is j hat, and it's 2.5. Sorry, I didn't put that 2.5. So how I would do this is I would do the multiplication first. So I would say 5 m 2.5, and then I'll say I cross j. I cross j is in order. I'm going to do +1, and then I cross j is k. Cool. And now I'm going to do j cross j. Well, that's 0. You know, we already showed that. Easiest, fastest way to do that is just do an ijk, and then just do 2 arrows in j, and then realize that you can't cross them into each other. You know what I mean? The cross product says, hey, you're gonna do j, like, hey, maybe this is my distance, but then this is my mass and velocity. So I'm gonna go distance into fingers this way, and then wrap it into I don't know. You could do like r cross mv. There you go. And then that would be a negative. Then you'd have a. This would be in the negative k. Okay, cool. That was horrible. All right, so cool. So we got this, and it's going to be whatever. Well, it's going to be I don't think. Oh yeah. It's gonna be 5 times 2.5. Yeah. 5 times 2.5, but then times 0.25 was our mass, and that's gonna be at 3.125. And is that what we got for any of them? Yeah, 3.125. So that checks. All right, hell yeah. So let's, and then but then check this out. So well, you have two components. You have one of the components that is in this direction, the I direction, but then the other component's in the J direction. Well, yeah, no doubt, we just talked about that. This is the J component, and then you can't cross it into the J component of the velocity. All right, so that's what we just showed as 0. So anytime that, hey, you're just like, uh-oh, like my radius isn't, you know what I mean? Well, one way that people do it is just like, well, go to the second one. Yeah, your distance to something's not going to be in a straight line, but hey, go find your velocity, and then whatever, you know, direction that is, and can you find something that's 90 degrees to it? Well, hell yeah, that's just going to be this, and that's going to be your 5. That's how you kind of turn it into a scalar. So we definitely want to double check this one though, like 100%. So we're going to have, you're going to have an I component crossed into a negative k. Cool, so we're going to have an I crossed into a k, that's going to be negative, and then we have a negative k. So it's going to be a positive j. I cross k is j, so we're going to get a positive j on that one. But we're also going to have a negative, we're also going to have this component of the radius, which is going to be a j. And so we're going to cross that into, and we're still checking this one. So we're gonna say, hey, this is negative, so we're gonna have the negative, and then we're gonna cross j into k. That is in order. We're gonna get positive j k I, positive I. But we did have that negative, so it's negative I. And then if we go back and then go over here and say, hey, we're gonna have a negative I component. Well, cool. That doesn't jive with our problem. It's not horizontal to this axis, and it's not passing through the left perpendicular to the rod. You know what I mean? So cool. We found a component that way. We found a component that way on that one. And I'm sure the same thing is going to happen when we go out to this one. But you know what I mean? We better double check it. So this is going to have a velocity in the negative I. Cool. So negative I is going to be, so here's our equation. That's going to be the velocity. Now the distance out here is going to be in the I direction, the J direction, and the negative K direction. Is that right? Yeah, it's in the negative K. It just doesn't look, it looks kind of funky. Okay, so we're going to have, so let's do the I direction first. So we're going to, I crossed with negative I. Well, it doesn't matter, I cross I is 0. Cool. So now we're going to do the J component. That's going to be a positive. So we're going to have a negative 1 times positive 1. J cross I. J cross I is not in order, so that's going to be negative. And then we're going to have J cross I is K. So cool. So we're going to have positive K for that one. Whoa! So we are going to generate some juice. Okay. So my bad. So we're going to generate some more juice in the K direction. And all of these other ones were in the K direction. Cool. So this, that's cool. I'm glad I double checked, because this will generate juice in the K direction. You know what I mean? It's a mass. It has velocity, and from our location right here, you know what I mean? And it's gonna generate some juice. Okay. So and what kind of juice is it gonna generate? Well, that's interesting that it's going to be a function of this height, which we don't know or something. They don't give you that height, and they assume that it's not even part of the problem. Oh. Here's why it's not. Because check this out. Then you're going to go over here. Check this one out. You know what I mean? They cancel. Because let's do this one. This one is going to be so we're gonna do the J direction. So we're gonna do a positive J. But then this is going to be positive k. So we're going to cross it with positive k hat. All right, let's do that. So let's just say we have positive 1 times positive 1. I always do the multiplication first, and then I do the cross product. I do j cross k. Well, hey, that's going to be in order. That's going to be positive. And I think I messed up something here. No, I didn't. Oh, no. Well, look at this. I don't even know what the hell I was even thinking. Because j cross k would give me a positive I. Yeah, I totally set it up wrong. Okay, so this is the mass that we're going to do the cross product. Pick our mass. Okay, it's got a tangential velocity in the I direction. So we're going to have positive I for the tangential velocity. Now the distance up to this, I mean, because to get to there, we're going to be in the I direction. We can't cross I's and I's, but we can cross J and I and get that K, and that's the one we're interested in. So we're going to go up that 1 meter in the J direction. And what are we crossing? Well, it's the distance. So we're going to cross positive J into positive I. Cool. So J cross I is not in the, so that's going to give us a negative, and it's going to be J, and it's going to be K. So there you go. And this one's going to be equal to that one. So we're going to have, this will generate a vector this way, but it's going to offset that direction. And it would just be interesting, I think, before we close this problem out, to actually get a value on that. But we can't because we don't know this height. But let's say we did. You know what I mean? It's fairly simple. We're going to have 1 meter times the mass, which would be 0.25 in our case. And then it has a velocity, and that's associated with this omega and this radius. See now our radiuses aren't the same. Cool, because we just did 1 times 0.5, and now we got to do omega, that's times 0.5. Times 2, that's the radius. All right, so that would only generate a 0.2. So if you confused those and added them, you know, maybe you get 7.5, and that's what you thought. So I think a better answer to this problem would be, I don't know, but I mean, obviously we're doing it from point mass, simplification, where a lot of people wouldn't do it from that. Okay, but I think we thoroughly, well, at least we covered the cross products, and I think that's a very good thing to do. Just because it's unique, because if I take the distance out to a point, like even just right here, like I can visualize this one. This distance crossed in with this, I can put this vector in the end, and I can be like, okay, that's going to be in the K. But then if I just go over here and say, hey, this distance crossed into it, well, it's like I'm no longer at the point that I'm actually, you know, but that's fine. That's just the way it works. You know what I mean? So that's kind of interesting how if you have a vector, your distance vector, and it's got two components, like one of the components, it looks like it's going to be not even, it looks like you're taking it about that point. But no, you're taking it about here. It's just a component of it. But in this case, these are in line anyway. And so these two would be 0. But let's say you were taking it to this component. Then you would take this value and then cross it. You would basically like lift this up to here and say, hey, there's the perpendicular, and now we can just multiply those straight up and get something in this y direction. And then you can say, hey, like let's just, you know, the other component's right here, so I'm just going to go right here and cross it in. And then when I do that, go that direction and cross it in. Hey, I'm going to get this negative I direction. And I'm going to go back to my location and say, hey, that's going to be the angular momentum from that point. And so let's just close, because I might want to call this video angular momentum is leverage of mass and velocity. Hell yeah. Alright, so thanks for joining me, and guess what? That's a video.